Hello, this is summary of lecture 26 of complex matrices and FFT. This is summary of particularly chapter 9.3 part 2. So previously we have talked about the roots of unity. We have seen that the W is the solution of this spatial equation, the z to the power of n equal 1. Okay, and we know, so we are familiar with the W, and we know that if once we find the first root, this one, the W, then we can find the other root of this equation by just simply having W to the power of the n number. Okay, so now I will introduce you to the Fourier matrix. So Fourier matrix, let me give you, it's a sum matrix, and let's say I'm interested in the Fourier matrix of n equal 4. Okay, so right now Fn, where n is 4, so what will I have here? So the component of F4 is the W to the power ij, where the ij is 0 to the n minus 1. Okay, so Professor Schrank also mentioned here, so we have to count from 0 to the n minus 1, which is what they did in the electrical engineering department instead of the mathematics, which counts from 1. So let me give that a reminder. So let's say this is column 1, column 0, 1, column 2, column 3, and this is row 1, row 0, row 1, row 2, row 3. Okay, so what do we have here? W to the 0, we have 1. W to the 1 times 0, so we have 1. W to the 2 times 0, so we have 1. And W to the 3 times 0, we have 1. So this is also the same, we have 1, 1, 1. Again, because W 1 times 0, so this W to the 0 and equal 1. Okay, and it's the same goes for the other. Okay, just to want to make that clear. And now we have W, and then we have W square, W cube, here W square, here W cube, W to the 4, W to the 6, W to the 6, W to the 9. Okay, and of course we already did this before, so we can plug all this number into here, and we have our Fourier matrix of n equals 4. Let's plug those number in. 1, 1, 1. We have 1 I square, I cube, I square, I fourth, I sixth, I third, I sixth, I ninth, and this is equal to, let's see here, 1, 1, 1, 1, still 1, 1, 1, I minus 1 minus I minus 1, 1 minus 1 minus I, 1 I. Okay, and then notice that the columns are orthogonal to each other. So for example, this and this are orthogonal. 1 and 2 are also orthogonal. 1 minus 1, 1 minus 1. This should be minus. I'm sorry. I to the 6, yes, this should be minus. Right? Yep. And this also 1 minus 1 minus 1 plus I also. And the same thing goes for the other. Let me check this column and this column. 1 minus I, 1 I minus 1 minus I, and then 1 minus I minus 1 I. Okay, and don't forget in the complex world, we need to conjugate them, so we need to change sign for one vector for the imaginary part. So let's change here, and then we have 1 plus I squared minus plus 1, and then plus I squared, and we have 1 minus 1 plus 1 minus 1, we have 0. So they are orthogonal, right, perpendicular to each other. So we can also, from using this property, using this fact, we can immediately find also the F4 inverse. Why? Because we know that each column are perpendicular to each other. So we can find the orthogonal of 4, which is the length. We divided all of this component by the length, and the component is square root of 4. Let me just put it half there. And let's rewrite the matrix as it is. Okay. And then, well, currently we already know that this is a unitary matrix, right? Unitary matrix, because they're all unit vector, it is square 4 by 4, and they're orthonormal columns. So we have the property of the Q4 Hermitian. Q4 is 1, and then we can find, of course, the inverse of Q4, which is the Q4 Hermitian. And then from here we can go back to the F4 by multiplying this by manipulating something in the length. You know, we can, from here we can get the F4 again. So that's it for the Fourier matrix. And now let's move on to the FFT. Actually, before moving on to the FFT, just want to mention that I just convert this F to the orthogonal columns, orthogonal matrix, I mean, but then we're interested in the F4 inverse, so we can easily use the formula, the equation from the book, if you just follow along. That basically what I have here, so this is 1/2 of the F4, right? It's F4, so we have here, this is also equal to like 1/2 of F4 Hermitian times 1/2 of F4, right? Because 1/2 of F4 and equal 1, so we have the F4 Hermitian. F4 is equal to 4i, and we can change it to the 1/4 F4 Hermitian to F4 is I, and we're interested in these matrix, and this will be our F4 inverse, is the 1/4 of F4 Hermitian. So probably this is more correct and easier way to find the F4 inverse. Okay, now I'm ready to move on to the FFT, but let me delete some of this first. Now, I will not go into too much detail, but we are interested in computing the y equals to fc. Okay, so in example of f4 here, we will have a vector of y0, y1, y2, y3, for example. We have the 4 by 4 matrix here, and then we have the constant here. Okay, and again, I will not go into details, but I want to focus on the time it takes to compute this form right here. So if you have 4 by 4, so usually you have 4 squared equation. You need to do this row by this row, so you need 1 2 3 4, 1 2 3 4, 1 2 3 4, 1 2 3 4. So you need 4 squared computation, and that can get really exponentially big as it goes to some bigger number, right? But we can make this faster. So the idea of FFT is that we want to do the multiplication of f times c as soon as possible. Okay, and normally we takes, because it has n by n entry, so we have n squared computation. Okay, but we can make this special by doing this some special pattern that I will introduce you. Using special pattern, we can reduce the time, and this is all what FFT is about reducing the time computation and computing faster. That's why it's called fast Fourier transform. Okay, fast. Okay, and the idea is to connect Fn with Fn over 2, so half of it. Okay, and let me give you an example here, a quick example, and I will not go into detail. Instead, I will just focus on the idea of FFT of computing faster. So let's take an example of F4. I will just blindly give you a formula here. I'm really sorry for that. This is identity matrix, diagonal, identity minus diagonal. Okay, and this consists of the F half of this, F2, this is the 0, and this is just some permutation matrix. And this permutation matrix will kind of like skipping one column each. This will be skipping. So what this does is that it will bring the even component in the C first and then the odd component later on. So like C0, C2, C4 will be bring out ahead, and the C1, C3 and so on will bring out later on. And there's an important thing here. This is the matrix of diagonal, right? But the diagonal here, so this is the D, is the consists of the roots of them, but this roots of the F4. Okay, so this is coming for Z4 equal 1. Be careful. I will put a really exclamation mark there, because this is not coming from the F2. I also got mistaken that this, because this is 2, I thought this is coming from the F2, but it's not. So in case of the F4, so the D2 will be the 0, the W to the 0, which is 1, and W is I, and the minus W D2 is of course minus I. Okay, so I just want to pay an emphasis here. So this is I coming from the Z4, not coming from the Z2, which is minus 1. Okay, yep. So I hope you see the idea here. So what happens if this is 16, right? Then it will be 8, 8, 8, 8. This will be 8 also. This will be 8. And then what better is just we can also break this down into F4 component, and then F4 we can break down into F2, and then you see that there are a lot of zeros here. So this matrix is really sparse, and you see that this is also identity. So just from that idea, I hope you can see that the computation gets so much faster. Okay, and I'll just bring out the number here. I'm really sorry that the idea of this is all about the recursion, and from 2 to the L we can bring down to the half n of L. So the L here is that, for example, in the case of n is 1024, so this is equal to the 2 to the 10, so this is L, and this is n, this one is n. Okay, so what was once required like 2 to the L, which is 2 to the 10. Sorry guys, that's why I feel something is off. So this should be for a size of 2 to the L. Okay, let me just give that a better color. For the size of 2 to the L, what was once need n squared computation, now we only need half of nl. Okay, so in this case, a really practical frequent example is we need a size of Fourier matrix of 1024, which is 2 to the 10. This is the L. So usually we need n squared computation, which is 1000 something computation, and this is really big number. This is bigger than a million or something, but now we can bring it down to half of nl and 10, which is just 5000. So that's really a drastic, a significant change, significant drop in terms of the speeding up the runtime. So that's the idea of FFT. I hope that's it, and yep, thank you guys.